Hi everybody. So my name is Franck Baudin from Qosmos. So I'm going today to talk to you about layer 7 matcher and contract metadata. Sorry. So, this work will leverage the NFQ and the contract that has been discussed before. So that's the first use case so that we would like to implement. So if it makes sense and if the design can fly. So few words of introduction about layer 7 classification and about DPI. So just for you to understand the requirements of a DPI engine regarding, let's say, a flow. So layer 7 classification, Layer 7 classification is based on two OpenFlow flows. It's client to server and server to clients. Because layer 7 classification is basically, okay, I want to recognize what is transported in this flow regardless of layer 4 up to layer 4 informations. So some protocols are recognized on client to server payload, some protocols are recognized on the reverse payload, and some protocol on the mix of both. So in this way, you have to correlate a client to server and server to clients, and this is exactly what the Linux contract is doing. So when you have the contract, you have a handle to both have conversation. Also, layer 7 classification requires IP reassembly and TCP segment reordering, because you cannot recognize a protocol if the payload is scrambled. So you need first to reorder it. So even if it's not very common on real networks to have a disordered TCP segment. So in terms of performance, so the key point here is most of applications are classified with the first packet of payload in one of the two directions I mentioned, right after the TCP handshake, but not before, because remember, the key part here is layer 7 classification relies on payload analysis. We absolutely don't care about up to layer 4 information. So some applications require more packets, so like Skype, BitTorrent to be recognized. And the signalization protocol also needs to keep going to be analyzed. For instance, when you have an FTP session which is open, so you can have multiple download that will start, so related conversation from a contract perspective. So you need to keep feeding for this specific protocol the DPI engine in order to say, okay, this particular flow is FTP. So I take one example with FTP, which is quite obvious for you. So also, sometimes the DPI engine failed to recognize what's in. So at some point, he said, okay, I just give up. And I stop to try to classify, and this is an unknown protocol. So unknown protocol is a protocol with an ID in our engine. In terms of performance, so this is not data center data, this is telco data, because we have customers in all spaces, but our biggest customers are in telco area, and our DPI engine is embedded in GGSN. So in GGSN, our return of experience is that 10% of the traffic is under classification at a given time, and 90% is already classified. So you just want to analyze 10% of the traffic. So the point is here we have an offloading. It's really like OpenVSwitch with userland and datapath. You have an offloading. So once the classification is done, it's done. You don't need to feed the engine anymore, except, like I said before, for FTP protocol and not FTP data. And to give you an insight about the performance, so on this Sandy Bridge platform, so with 10K conversation per second, we can handle 4 gigabits with 1 core, 2 hyperthreads. Okay? So here is the contractor we talked right before. And this is the NFQ, and this is already a use case of this new framework. So the idea here, so I've got a caption. So in blue, this is a layer 2, layer 4 matcher, And in green, this is layer 7 matcher, and I will explain that after. So first, so the first thing is to do is, okay, you have a L2 matcher protecting the contract action and the NFQ action you have seen before. So the idea here is to attach a contract to the escape-off, and then the packet is mapped with the corresponding contract ID and sent to the L7 engine. So the L7 engine has a contract ID, is doing the analysis, and when the analysis is done, it will put it back asynchronously and save the result in the contract mark. So this is, and it corresponds to the con mark matcher, CT mark here. So when a packet arrives, first, it has no classification. So from input port 1, we attach a contract, we send it to userland, and at this point, we don't know, the contract mark is still 0. We recirculate, and the first packet won't match this one. But at some point, the DPI engine will finish its analysis and update the contract mark saying, okay, this is FTP data, this is SSH, this is BitTorrent. And when this is BitTorrent, okay, let's say contract mark equal 5, okay, I can choose the proper action. So all actions are available. So throttling, firewalling, anything, rerouting. So what I want to show here is how we have to build up the rule hierarchy in order to avoid loops and to maximize the performance. So the key here is to attach the application ID, the classification result in the con mark, and to retrieve the con mark as soon as possible in order to match on this con mark. So again, so in green, L7 matcher, in blue, layer 4 matcher. So the highest priority rules has to be feed the contract, because no contract, no con mark, no con mark, no match. I mean, you need to attach to the escape-off the contract. So you go through a contract and you feed the DPI engine or the application. Based on the results, you can go too low. So maybe you have to recirculate. This has to be defined, but at this point, you don't need to recirculate because, of course, this will be in progress because here you have the packet, you send a copy of the packet to userland or a reference, but you keep going. You don't wait for any feedback. This is an asynchronous feedback. And you can go to the low priority rules, and the low priority rules are based on L2, L4 matching, which are the default rules. So keep in mind that layer 7 classification happens after TCP handshake. So the idea is, okay, so you feed your layer 7 engine, and as soon, and for some time, let's say 3 packets in each direction, you won't have any verdict. So you need to have some kind of rules, which are regular rules like today. And then at some point, you will know, okay, this is SSH, this is BitTorrent. And then, okay, you can classify directly and do what you have to do. So the idea is to have layer 7 rules with higher priority than layer 4 only. Of course, here you can add layer 4 also, like you can do this per VM, like with this kind of port, because you don't want specifically, you may not want to have layer 7 classification for all ports. So, one example of the rule sets. So just back again, so we have high, medium, low. So the first one is to keep updating the contract and the DPI engine, then layer 7, and then layer 4 only. So this is the most basic layer 1. So input port equal 1, so highest priority. I didn't play with table in this example, so just here, yeah. So at the beginning, the con mark is 0. So I'm assuming that the matcher is implementing in a way that we have to discuss, which is, okay, when I don't have any contract, the con mark is 0. The con mark is a CT mark, okay? So I don't want to do an arrow CT here, an arrow mark here because my SKB is null. So this is to avoid the loops. So if you have a packet that is already classified, so with a con mark different 0, so you won't match this one, you will go directly here. And then you will have BitTorrent, Skype voice, etc. If the con mark is 0, you feed the contract, send to NFQ, so you can use different kind of queue in order to do multi-threading or whatever. And at this point, you're sure that the DPI engine did not do its job, so you can just skip all of these rules and go to table 128. So that's an example. If you recirculate, you will just not match this one. You will start to match here. So just before trying to go beyond, so I will try to summarize. Layer 7 classification is to give you an insight about what is the flow bud. This is SSH, this is BitTorrent, and you want to match on BitTorrent, but you cannot match as the first packet. You need to recognize it first. So that's the point. Also, this classification is related to the two-way conversation, to the contract. You don't care if it's server to client, client to server. This is the same protocol. SSH is SSH. So that's it. And then I try to... So what do we have to do? So we have to use a contract mark in the examples before, but as a developer cannot stop, I was thinking, okay, how can we go further? So this is not related exactly to Open vSwitch, so this is related to kernel development. So today in the contract, we have one placeholder, which is the contract mark. I say, okay, today contract mark is 32 bits, but we may want to have more registers to store metadata, per flow. So users can store metadata like, I give examples of what can be a metadata. So layer 7 classification, subscriber ID, SLA ID, policy ID to apply. Because at some point, you don't care if it's Skype or whatever. You can have an application that say, okay, my engine will give you two values, or three. 0, 1, okay, it can pass. 2, you have to rate limit. 3, you drop. And all the intelligence about the very complex state machines stay in user land. So that's a way. So that's why an application ID is just a way of giving you a classification on which you can match. So either you have very few rules that you will push in OpenFlow, and that will be optimal in terms of because at some point it will be tightened to an action. I want this flow to be rate limited or dropped. Also, we are talking a lot about service chaining, and service chaining requires service path, service index, and metadata. So this metadata could be stored in the contract also. Then I'm thinking about my old friends and people doing some edge distributed firewall. It has nothing related to DPI, but at some point you have a bunch of machines running a distributed firewall, and you want to store a unique ID for this firewall, and 32 bits may not be enough. So having these kinds of scratch pad in the contract may help, and having the ability in Open vSwitch to load the content of this metadata could be that's a really nice toolbox, and I think it could be very performant in the way that once the classification is done, you don't have to go through user land again. So, and in terms of OpenFlow extensions, so it would require con register extension, and in terms of action, we can think of reusing the code register to load the NSH value for the NSH encapsulation. That's an idea, even if it's not the first target. Do you have any questions? I've been quick.
This is Hamid from Broadcom. Where can we get the copy of the slides presented here?
I'm planning to post all the slides on the Open vSwitch website following the conference.
I was wondering whether you could just clarify how the mark is updated from user space, the con mark. Yeah, my name is Roxana.
Yeah. Okay. Yes, I've been a bit quick maybe on this slide. So, so for this, this is an mmap, and here you can update the. You have a netlink message that permit to update the contract fields. So you just give the new values and the contract ID, and you can put any value in mark.
We have plenty of time for questions if there are any more. Can you identify yourself?
Hi, I'm Radhika. Since you said L7 classification is based on the payload, so here the CT NFQ goes to L7 and comes back. Does it cause any extra delay? Can you talk about some payload and delay factors?
So yes, it does. So it's extra processing. So you need to get a reference via mmap of the payload and then to analyze the payload. But it does not create a lot of head of line as here you have to notify the user land that you have to wake up the socket, but the processing keep going and you recirculate immediately. So this is why the idea in this design is not to create head of line. So just to repeat what is head of line. So let's say you have just one core processing all of the packets. You don't want the first packet of a bunch of 10 to slow down the others which are behind. So this is why this is a non-blocking action. And even the first packet here is quite fast. So you just get a reference to the L7 engine, and the L7 engine do its job at the speed it can do. And in the worst case, if it's overloaded, it can just let the con mark at 0 or put unknown, something like that, some kind of defensive value. So in order not the system to collapse. So this is why so this is how it works. And just to go back on performance, just a few words on this one. These 4 gigabits are obtained with a pipeline model, which would be the same that we would use here. So you have a DPDK thread that is doing the I/O, and then you have a core which are running the DPI, consuming a DPDK ring. So you have 4 gigabits, so you have the I/O included. So that's the cost. And if you take this example here, you're going to have a dispatching here. So either with different queues chosen here, or either you will have something very, very clever in terms of implementation and think that this implementation will work and should have good performance in kernel, but also can be implemented very easily in DPDK, with DPDK datapath. So in that way, with DPDK datapath, so here you have a first process, and here you will have a secondary process with DPDK and a rig in between.
I was about to add one point. Okay, I'm Thomas, Nora Networks. One more thought about what you just presented, since we talked about this a lot over the last couple of weeks. Essentially, the performance, if you have the asynchronous model, should be the same, because what happens when you send the packet to user space, it creates a clone of the packet, which is for free. It's because due to TCP usage of SKBs, you can do one clone for free inside a kernel. It will continue processing the packet in the data path, but in parallel, it will send the copy to user space, and it will keep doing that until classification has been reached. So it will copy between 1 and some number of packets user space, and once you know which class to assign this flow to, you will update the CT mark to give feedback to the OVS data path to continue or to start classifying packets based on that mark. So essentially, performance will be the same, but you will spend some additional CPU cycles on the actual classification. So that is the async model. And the other model is that when you want to block traffic and export or outsource the classification user space completely, you would essentially wait at the NFQ box right there. The packet would be stolen by the user space application. It will be will get re-injected. That's what I mentioned in my previous presentation. It would go back at the beginning of the OVS data path, and that will obviously have severe performance implications because you go to user space. The performance will be, I would expect to be the same as an OVS slow path hit right now. So it goes user space back, and you start all over.
Thanks, Thomas. And by the way, thank you for giving me a lot of hints on the design and presenting the NFQ. I think that's how things work. And so this is a use of a new framework in developments, and there should be other use of this, some kind of external rule engine that will decide what should be done for the packet, and anything can be done.
And so if you can identify who you are and your affiliation, that would be great.
Hello, so I'm Emre Altan from 6Win. And thanks you, Frank, by the way, for the explanation about DPDK. The question that I have, I think it may concern the three of the presenters about NetFilter and DPDK. So because DPDK, the data plane development kit, is running on user space, how this will interact with IP tables, knowing that IP tables is directly linked with the kernel and NetFilter. How is the link between DPDK and IP tables is done?
So well, just to be clear, that all the contract stuff that we've been talking about is actually not using IP tables. IP tables can use contract, but they're sort of unrelated. And so the whole point of DPDK is that it bypasses the kernel. So none of that's available if you're using DPDK. So there would have to be some sort of recreation of these abilities to do it on DPDK. But that's why I was saying that we're trying to make it so the API is not Linux specific, so that people can create their own versions of like a connection tracker and then make that available.
If you think of the NFQ, you can map it on the DPDK rings, a bunch of rings with an index.
Actually, there's one more option that you can have. You could use KNI to feed it back into the kernel, run it to the contract, or export it to user space. But you obviously lose a lot of the benefits of DPDK, so that would be a short-term workaround maybe to get it to work, but not a long-term solution.
Johan, do you have a question? Johan Tenzing from Metronome. Could we jump back to the slide you had with the performance, 4 gigabit per second, etc.? Yeah, the rule of thumb we've always been working on for the last number of years was approximately 10 packets per flow. So that refers to a microflow. And I'm actually interested to unpack these numbers a little bit, because if you're saying the 4 gigabit per second is what you can get per core, I'm assuming that is the 10%, which is still being classified, is now the 4 gigabit per second. And therefore, the total traffic on the network would then be 40 gigabit per second, and per core, obviously. But now if we say that only equates to 10K conversations per second, at the 4 gigabit per second, that, with my simple math here, that equates to millions of packets per second at a small packet performance. So we seem to be either assuming very long-lived flows here, or we have some misunderstanding about the average packet size. So could you just comment on the length of a microflow that you're seeing with this data?
So first, this is to give an insight about what could be done today. So this is for 100% of the flow. So Just the 4 gigabits on 2 core is you inject telco traffic in a DPI engine through a ring. So if you take back this design, so you can expect to have per core here 4 gigabits. That's the purpose. On telco traffic, on data center, I think it should be much more, because the classification would be far easy. It depends on the problem with DPI is it really depends on the traffic. So if you have 100% of BitTorrent, it's more packets to analyze, the performance is dropping. If you don't have a Skype or BitTorrent, the performance rise. So that's why we have trouble to explain the performance. But this is a typical telco that you have in the GI LAN, so between the GSN and the internet. So this is the performance we can achieve on Intel.
But again, is that the performance while you are doing the 10% which is being classified and analyzed, or is that the performance of the total of the 10 and the 90%?
It's the performance of the overall.
Okay.
In this example, knowing that with good optimization, it should rise. Because, okay. I wanted to give a perspective to say, okay, how will I dimension so I've got already like 2 cores for my DPDK or for my kernel data path, and how many cores to do DPI and to be. You don't want to do DPI on all links. You have an action that protects, and you can target specific ports, for instance. Mm-hmm. But anyway, you can have also better DPI engines.
Okay, and then could the others maybe comment? Let's say we have a 40 gig link with one direction of small packets would be 60 million packets per second. And then if we have that 10 packets per flow rule of thumb that always used to be used, you would have 6 million microflows per second for that unidirectional 40 gig link. So what kind of performance are we seeing currently, let's say, with the netlink messages per second, or with contract per core, etc.? It was a little bit hard to understand from the earlier presentation of the actual microflows per second that's being observed today.
Does it work? So the number, this is Thomas again, the number is, for connection tracking, is about 6 gig. So it's well below the numbers that you just pointed out. But so certainly something that we're all interested in actually improving. At least that's the numbers I've been gathering. Maybe it just is.
Well, the numbers that we were showing, and once again, these were like preliminary results, but we were able to pass 10 gigabit per traffic through the connection tracker. But I think Johan's question might be a little different. I mean, that was one aspect of it, but I think you were also asking about having basically microflows, right, and missing. So a lot of it depends on how you end up writing your flows and how well megaflows end up covering them. So if you had lots of short-lived flows, but your policy was such that that you weren't matching on, for example, the source and the whole 5 tuple, then a megaflow would be able to cover that, and you wouldn't require missing up into user space. However, if you did, if you had a policy where you wrote lots of different rules over source and destination TCP port, and then you could end up with situations where you're missing a lot more and going up into user space. And we do some things to try to optimize that. So we look at we do wildcarding of the actual mask of ports, so that it really depends on your policy. But I mean, ideally, you're not requiring a lot of packets going up to user space. And I think that for the most part, we should be able to cover that, except for in extreme cases.
All right. That's the end of our morning session.